this was entitled an unboxing of the DVL, so why don't I begin there? I don't have a box to take the DVL out of, but if you had, you would see it looks something like this. And usually what it follows along with is an Ethernet cable and a serial cable. That was Zoom magic. And what I'm going to do today is show you how to configure and test out your DVL. So the first step is connecting to the DVL. So I am going to connect to the Ethernet. It's probably hard for you to see, but on one side it has an E for Ethernet, and on the other side it has an S for serial. It's probably worth it to tell you at this time that this is composed of 4 transducers, as you can see here. In the center here, we have a temperature sensor with this brass plate for thermal conductivity. Pressure sensor here, which is with the holes for the vent in communication with the background water. And on this side, we have an LED, and you'll be seeing that blinking in a moment once I have connected. So with no further ado, I am going to connect. So the power is already connected to the DVL. And as soon as it starts connecting, I don't know if it's possible to see this, but yep, you can see it's already blinking. So it starts blinking, it starts operating in its last valid configuration. So it's pretty much always in measurement mode unless you're configuring it or downloading the data. So it's powered up, it's blinking, it's operating. Let's connect to it now. So what I am going to do is share my screen here. So the first screen I'm going to show here is this one. And as you can see here, these are my network configurations. This is in the Microsoft Explorer window. So if I just simply, you can see here we have development DVL 1000 with a serial number. And as I meant to say also, this particular unit that we have today is I got to get camera over here, is a DVL 1000, 4,000 meter rated. So if you were curious, we also have DVLs, similar one for 300 meter rated and a DVL 500, which is a 500 kilohertz. All right, so if I double click on this, this should take us up to the web browser interface. I'm going to move this over here so that I'm looking more directly at you. And you can see the different configurations. I should basically step back and say that when you're connecting the DVL, if you connect the Ethernet directly to your computer, it can sometimes take a little bit longer time for it to identify it on the so-called network. Right now, I have the DVL connected to my Wi-Fi switch, and when it's on the network, it registers the IP address much more rapidly, so it was able to find it and show it. If you're connecting with serial, then it is just basic serial communications. So if you have an emulator, then that should work perfectly fine. But I'm not going to spend any time on the serial communications. This is really about the Ethernet and how we configure it through this web browser interface. So let me make sure that I'm sharing the correct window now. Let's see. Let me change some windows here. I believe I'm sharing the correct window. Let me try that. Yeah, that's the one I want to share. And move all the faces away. Okay, so I'm assuming if I'm not sharing the window correctly, please somebody contact me immediately, but I assume I am. So what we have here is the web browser interface. And at the very top bar here, you have the identification of the instrument's name, the IP address, the frequency of this instrument serial number, and the firmware. Just for a basic layout, on the left-hand side, you have the different pages which we'll interface and go through in a moment. And then on each page, you have a menu of selections that you can configure their instrument for. And each one of these configurations here is described in this help menu to the right. So if you have any questions, you have your help right there available for you. So the first place that we start is the measurement configuration. So this is how we configure the measurement modes. So the DVL configuration, we first begin with the trigger mode. So when we talk about trigger mode, is we're talking about how it's instructed to ping. So there are basically two modes. You either externally trigger the instrument, or you use the internal triggering. So this symbol here, instra, means it's internally pinging, and it's the most common way that we actually use the DVL. However, if you have instrumentation that conflicts with the DVL and you're sharing acoustic space, sometimes what you want to do is trigger externally so that you don't interfere. So then you can use the external lines, the TTL lines, or the 485 lines, and you can either use the rising edge or the falling edge, or a combination. You also can use a serial input to determine when it triggers. So what we're going to show today is the internal triggering, which is the most common. The next thing is the sample rate. And for this instrument, you can see you have different frequencies at which you can ping. I'll just set it for 4 Hertz for now. The next is the configuration of the speed of sound. So what we use for a speed of sound to estimate the velocity. This will scale the velocity that we'll be using. So the default is fixed, which is set at 1500 meters per second. And you would use this if you have an external sound velocity sensor. So if you have a requirement for accurate navigation, then you'd want to use this because you'd have an external sensor that accurately measures what the speed of sound is. Alternatively, if you don't want to use this, you can actually estimate what the speed of sound is from the instrument itself. And to do this, we measure the temperature and we use the salinity estimate, which is just below this. So you have to have a pretty confident estimate of the salinity in order to get accurate sound velocity estimates. Okay, so this is the instrument configuration. Now let's talk about the bottom track configuration. The blanking distance is basically where we start looking for a return. So right here we have it as close as possible, which is set at 1 centimeter. And then we have the maximum range here. It's important to note at this point that the range is coupled together with the sample rate. And the reason for that, there's only enough time for a ping to travel out from the instrument to the bottom and back again. So we're limited by the speed of sound and the distance. And you'll see here on the right-hand side, there's a table that indicates the different maximum ranges for different ping rates. So you can see for our 4 Hertz ping rate, we have the maximum of the instrument, which is 80 meters. But if we were pinging out towards 8 Hertz, we could only go out to 61 meters, roughly. So we'll just leave it at 50 meters for now. Under this, we have the transmit power. Generally speaking, we always keep it on maximum unless you have power consumption issues. Then you can use a user setting, and it goes from the minimum output power to -20 up to full power, which is 0. So this indicates how much you are going to attenuate the output level. Under this, we have the bottom track data format. And you have here is the DF21, which is Nortek's data format. And that's a much richer data format than you're going to get with others because it has estimates that help you with precision navigation. And there's 2 of these. The first is the time at which the ping is on the bottom. So when you know accurately when the measurement is made, then you can best synchronize it with an INS system. The second thing is it includes a quality parameter for each and every ping. So this is what gives us much better navigation possibilities. But you can see in the drop-down menu, you also have some of these legacy data formats like PD0, 4, and 6, and then a selection of NMEA data formats. These are all in the manual if you want to browse that. Okay, after this, we have the option to enable water track. And the cool thing here is that if you use water track, we use the same ping for bottom track as we use for water track. So it costs you nothing. You don't have to compromise a bottom track ping for a water track, which is common in a lot of DVLs these days. So with this, you get more information without any extra cost. And then much like the bottom track, we can choose our data format that we like. And we're gonna, again, keep it at the Nortek format. If the instrument is licensed for current profiling, then you can enable it here. And then it functions much like an ADCP does. So basically you select the cell size, blanking distance, the maximum range over which you want to profile, the velocity range along each beam, transmit powers and coordinate systems. And then again, the data format down at the bottom, which has, again, Nortek, NMEA, and a PD0 format. The one that I jumped over here was the interleave ratio. Now the interleave ratio tells you, since you're not pinging with the same type of ping that you use for a bottom track, it's actually a different ping. You have to interleave in the profiling ping. So if we set it to 2, that would mean every other ping would be dedicated to current profiling. If we set it to 20, then every 20th ping would be a current profile ping. So for the moment, we're going to set it at 2, and then we're have the measurement configuration complete here. So some comments at these buttons down at the bottom. So now that you have a configuration you like, you can save this if you want. And you also can use that saved configuration and upload it if you have one that you want to consistently use across deployments. Reset button basically takes you back to what is actually currently on your DVL. And then set defaults is there's a default setting that the instrument might have if you're unsure. And then finally, we have submit. Submit basically takes this configuration that we've just made and sends it down to the instrument. And if it likes it, it'll give you a confirmation here. So it says configuration complete down at the bottom. Now, if I did something, let's see. If I wanted to go 8 Hertz and 80 meter range, which is not permissible, as we've seen in the table over to the right here, and we try to submit this and send it down, then what you should see is an error message down at the bottom, which tells you why it failed and the correct range of values that you can use. So I'm going to set this back now to 4 Hertz, and I think it was at 50, so that we have a valid configuration. And configuration complete. Okay, so let's march on to the next page, which is the instrument settings. So here you can set things that are particular about the biases and offsets to the instrument. So the mounting angle, if you have a known mounting angle that you want to correct for, then you can rotate it by setting it here. You can also set the pressure offset in decibars. You can also turn on and off the LED, so you can turn it off or turn it on after 24 hours. And then for the serial communications, you can configure the serial communications, whether it is 232 or 422 protocol, and of course the baud rate. Now, diagnostics here is a term we use for the recorder. Basically, if you want to record data from your measurements, so the configuration that you've just made, you can record it to the onboard SD card, micro SD card, and you just need to enable it and put on some sort of cool file name. And we'll submit this again. So it's going to temporarily interrupt the currently running measurements, and we're okay with that. So we'll say yes, it's going to process, and then say that the configuration is complete. Excuse me. It is also say that the recorder is now enabled, just so you know that you are filling up your recorder. So that covers this page. We'll move on to the next page, which is additional data formats. So with one of the advantages of Ethernet communication is that you can send out different data to different addresses. So you can see here you have different baud track formats, and water track and current profiles, and you can send them to different addresses. And you can also send this to UDP data transmission, which is a broadcasting protocol. And here you have the client addresses and the ports. You have two additional data formats, an A and a B. I'm not going to mess with that today. And let's see, display data. I'm going to come back to that because that is how we're going to test out the functionality of the instrument. So here we have the network configuration. So this gives the name of the instrument. So you can go in here and change the name. This one is called the development DVL. And it has an IP address assignment, which you can either set to static or dynamically assigned. Static one you can configure here, and if you have UDP transmission on this, prefer to have UDP, you can enable that as well. Then finally, down at the bottom here, we have the time synchronization. And what this is that the DVL can actually be synchronized to an external server using the PTP or NTP protocol, which is a much higher level of synchronization. Again, I'm not going to do that because I don't have access right here to an NTP server or a PTP server. Next page is the maintenance page. And here you can set the clock on the DVL, where you can set it to local time or UTC. Straightforward. Then you have the system information, which gives you the name of the DVL and serial numbers and firmware. So you'll see, since I am connected to the outside world at the same time of connecting to the DVL, it can check to see what the if the firmware is up to date. And you can see that the firmware on board applications and documentations are all up to date. You will also have access here to see the release notes. So if you're curious about what the last changes were since with this release that you have, you can click on here and it'll take you to that link will take you to the release notes. Below this, we have a series of buttons where you can update the firmware, you can check for updates, you can erase the SD card here, you can reformat the SD card, which is a natural step often in the firmware upgrade. Rebooting the system, which is a step you also need to take when you upgrade firmware. You can retrieve the support file, and you can update the applications and the documents on board the instrument. One comment about the retrieve the support file. This is actually quite interesting to know because when you are having issues or uncertainty about your DVL and its functionality operation, you can send us a support file, and in this contains all the system logs and other measurements. But when you do this, it makes sense to actually first put the DVL in the water and then hit the button that says retrieve support file, because then we'll make a quick measurement of the system so that we can review that as well. So speaking about these logs, we also have, you can retrieve these individually by getting the network log, deployment instrument, and system logs. And you can also input entries into the deployment log so that you have, we are on site at this particular location. Next, we have the page for security, and this basically allows you to put a password on the DVL. So if your DVL is on a system that many have access to, you might want to password protect it so people don't change the configuration or monkey around with it otherwise. Let's see here. Next, we have download data. So you can either download data in two different ways, the HTTP or FTP protocols. I'm going to stop the instrument to download the data, and it's going to show me the different files that we have recorded. So I have a couple one that's going now, which is cool file name, and some other ones from earlier today. And this is just click on this and download. So it's standard HTTP. Then finally, we have the applications and the documentation. So with the applications, you'll see that there are 2 applications that we standard ship the DVL with. And the first is called the Nortek Discover. And this program allows you to discover the DVL. And the advantage of this is that if it's a static IP or dynamic, it'll still find it. So you can always find the DVL with this application. The MIDAS application is something we reserve for our more advanced users who are system integrators and want to have greater access to the DVL and to actually visualize the data that they're looking at. MIDAS is something that we commonly use out in the field when we're testing the instrument. So it's a real-time application. And then finally, the documentation down at the bottom. So on this page, you will have the quick guide, the DVL operations guide, and the system integrators guide. These are the 3 PDFs. So I told you we're going to jump back to the display data because that's how we're going to do the functionality test. So if I click on this here, then what you're going to see is a real-time display of the data. So you have the bottom track. You have the text, which is sometimes easier to just view if you're trying to home in on one particular beam or the pressure, for instance. You have the water track values, text again, and then the current profile. The current profile is actually, when you're doing a functionality test, might be the most interesting one to use because you can see basically a response with the amplitude. So I have beside me a bucket of water that's filled to about 30 centimeters high, and I'm going to take the DVL now and dunk it in it. So this is how you would do a functionality test. So as you can see, it is still running because the blue light, hopefully you can see, is blinking. We're going to drop it in here. So you can see the amplitude goes up as well as the correlation on the right-hand side. And you got stable velocity measurements out to 6.5 meters. So you're just basically looking at signal bouncing around in here before it drops off completely because there's no scatterers in this fresh water that I have. Now, if I can manage to move over to bottom track, you can see that this is actually working well at this particular moment. So you have velocity, figure of merit, which is our quality parameter, and this is a measure of standard deviation for what we expect for our estimates. And then we have the distance, and that should indicate how far away the bottom is. So if good, it looks like it's actually detecting the bottom more or less 10 or 15 centimeters away on all the beams. I'm actually surprised it's that much agreement. And then we have velocity estimates along the beam and in the X, Y, and Z. And up at the top, we have the pressure. So if I just move this up and down, then we should see the pressure signal go up and down, and that's lovely. All right. So that's how we do a basic functionality test. Now I've taken it out of the water and the signal should be more or less gone. So that effectively is a walkthrough of the connection and configuration of the DVL, and then just a basic functionality test at the end.